Okay, now today we are going to have a look at the processing, different types of processing on the material, and how does it affect the properties of the materials. Different type of processing that we perform, the general type of processing are casting, forging, rolling, machining, and heat treatment. Now these processing have an effect on the microstructure of the material. Now if the basic microstructure of the material change, the material properties will change. For example, strength will change, hardness value will change, ductility will change, and so on. Now when we pour the molten metal, let's talk about the casting. When we pour the molten metal into any mold, the freezing starts. Now initially the temperature will drop, the metal will start to cool. It will reach at this point A. At this point A, the freezing of the metal will start. The temperature will be constant until all the metal has frozen. And after that one, the metal start to actually cool down. From that point up till here, it's all liquid. From point A till point B, it is the mixture of liquid and solid. And after point B, it's going to be all solid. It depends on your cooling rate, how fast you are cooling. It depends on the size of the component you are casting. We will have a geometry of the component. We will have different types of grain structures. So these grain structures which will form after the material has solidified, which depends on the rate of solidification, will in fact at the end will affect the properties of the material. Okay, now let's go to the next one. Now the solidification time, when you pour the metal into a mold, during the early stage of solidification, the thin layer is going to form at the cooler mold, at the outer surface. And then the inner will start to actually solidify as well, which means the rate of cooling at the skin, the outer layer, is a lot faster than the rate of cooling in the middle. Now, if it's like cylindrical, you can say like the top, the outer layer will have a different microstructure as compared to the inner layer, because the faster cooling, the grain structures are small. Slower cooling, the grain structure are bigger. When you slow cool something, it gives the grains a lot of time to cool, a lot of time to grow, so they grow. And the grain structures are more coarse. They are a lot bigger. If the surface area is greater, the faster the cooling is. Now, we got a law, Chovorinov rules. It's given by Ts equals C, where C is constant volume divided by the surface area to the power n. Where C is the constant, it depends on the mold. Are you using aluminum? Are you using like cast iron dies? What kind of mold you are actually using? And the n has a value between 1.5 and 2. Okay, so that's the cooling curve here. Now, let's have a look at how the material solidify. When the material solidify, the dendritic solidification happen. Now, what is dendritic solidification? Dendrites are the structure which looks something like that, like these kind of grains. They will form. They will initially start to form next to the mold wall, next to the surface where you are actually doing the casting, and they will try to grow inward. The growth of these dendrites are usually towards inward. If this is a cylindrical object, the growth will be inward towards the center. Metals closest to the mold will solidify first. then dendrites grow from this initial solidification. Now this will lead to a casting that is non-homogeneous. That's non-homogeneous mean it will have a different properties at the outer surface, it will have a different properties in the middle. So we will have different mechanical properties. Now what effect the dendrites have on the casting? There is a phenomena which is known as segregation. Segregation is a property of usually occurs when the material is solidifies from liquid to solid. What actually happens is the structure that solidify first have a different composition as compared to the structure that solidify at the end, at the final. If we got a very thin sheet, the properties will be fairly similar wherever you just measure the hardness. But if we got a structure that's cylindrical, very thick, and the cooling rate is not uniform, the outer surface solidify first as compared to other, then the material will have different chemical composition at the start and in the end. Now then there is a microsegregation which occurs over a distance comparable to the size of dendrite arm spacing. Now dendrite arm spacing is the spacing between these two dendrites. Yeah, so that's the dendrite arm spacing. Now then we got a macro. Macro segregation occurs over similar distance to the size of casting. Now this can be caused by many processes. We will have, when we do the casting, after the casting we have shrinkage. It also depends on the density of the pouring liquid. It also depends on the temperature as well. We do not want segregation, we want uniform properties. We need to get rid of these segregations. So microsegregations can be removed by a process called homogenization. Now homogenization, you heat the material at a certain annealing temperature and you kind of leave the material at that temperature for some time. And what actually happened, the process, the impurities or the different properties, different type of properties, different chemical composition, different atoms, they try to move uniformly in the structure, in the form of the solid. They don't convert into liquid, and hence we get rid of microsegregation. Macrosegregation are the issues. They cannot be removed, but what we can do is we can control the casting process and we can sort it out during the solidification. We can add the electromagnetic stirrer, which can just make sure all the liquid is moved, mixed uniformly. Sometime we actually, when we are doing the casting, around the casting we have an ultrasound which actually breaks the dendrite, just like it breaks the calcite or calcium that's formed on your teeth or anything like that. So it kind of break that one, which will convert the macro segregation into micro segregation, and micro segregation we can get rid of that. Now let's have a look at this case. Imagine this is the mold and we pouring a liquid metal into it. When we pour the liquid metal into it, initially at the surface you can see at the mold wall, what actually happen is the dendrites, the crystals start to form, because this is known as the chill zone, which is the temperature is much very low as compared to the temperature of the metal. Now the grains are going to grow inward direction. After that one, you can actually see the columnar zone. The next zone is known as the columnar zones. We can see the crystal structure try to grow all the way inside. Now this is shown by one of the other diagram. Let me just set. Now here we have a look at that one. The first, at the boundary, you can actually see this is a chill zone. This is the first solid that's formed, and it consists of the grains. They are heterogeneously nucleated grains, so they are quite small as compared to the other. Now, then after that one, you got this columnar zone where the columnar grain structure is formed. So they are like bit longer, bit bigger grain. Yeah, and they are aligned in the direction of the cooling. So they are aligned in the x-axis, parallel to the direction of the maximum temperature gradient. And these grains grow towards the center. So if you got a piece of casted object, you can actually look at the microstructure. You can tell the outer layer and the inner layer just by performing a microstructure analysis. Okay. Now, then we have the molten metal, which is poured, let's say, is from this direction. Okay. Now, okay, the process of sand casting. So initially, we place the pattern in a flask and pack it up with sand. Next step is we put the other half of the mold on the top. Again, starting with a wooden or metal frame. Then we just put some sand, and we make sure the sand is properly compact. So we just compact the sand by using some wedge-shaped rammer. And we add more sand. We perform the same operation again. And then we actually ram it. After do that one, we level the sand. And we need to drill some holes. So where we can pour the molten metal. So we need to make sure we do it carefully. It doesn't damage the structure. Now, one is called the runner and the other is known as riser. Runner is where we pour the liquid, and the riser is where it's going to rise. Now, then we create the small holes. The reason we create the small hole is when we pour the liquid, it might react with this material inside the sand, and then it will produce the CO2 gases. And these gases need to get out from the mold. Otherwise, the mold imperfection can occur. Then we separate the two halves, take out the mold, and then we put them together. Now, sometime inside we can put like a solid graphite powder, which act as a lubricant, which act like a separating material. And then we pour the liquid metal. So this is the runner, and these two are the risers. We design in such a way that when it's tried to solidify, you can see on the runner side, there will be some shrinkage. So we actually add the shrinkage allowance. Then we open it up and we remove our structure casting. Now these are the top and the bottom, and then we got the casting here. Now this is the runner where we put the molten metal, and you can actually see it kind of sink in, which shows the shrinkage cavity. Now, the disadvantages of the casting process is a highly laborious process. And if something goes wrong in terms of the cooling rate, you have to remelt and redo it. The other disadvantage is the surface finish is not very smooth. So you have to perform a secondary finishing processes. Now, the properties of the castings are influenced by the potential defects. Which can occur because of dendrites, which they can be inclusions, they can be porosity, or it can be because of shrinkage. Now, this will affect the overall defects of the materials. Now, to do that one, we need to design our mold in such a way. We need to actually emphasize on the cooling rate, or we need to change the composition of the casting or the metal or the material.